Right. So first of all, thank you for being interested in my Qcrypt 2022 submission, Quantum Cryptography for Quantum Metrology. Currently, I'm a postdoc at CQT in Singapore, but the bulk of this research was done at l'IPSIS in Paris during the last year of my PhD under the supervision of Damian Markham. So right off the bat, the title may seem a little bizarre because cryptography and metrology are probably considered to be non-overlapping disciplines within quantum information. Metrology is concerned with the task of estimating unknown parameters, whereas cryptography is concerned with security and privacy and what have you. So it's hard to imagine what kind of role cryptography could play for quantum metrology. But in fact, there are many scenarios in which the need for cryptography naturally arise. In multi-party quantum metrology, one of the parties may be untrusted. In any sort of spatially distributed estimation task, which information is communicated through quantum channels, a quantum channel may be unsecured. And both of these are prominent and exacerbated within quantum sensing networks, which are becoming increasingly popular. Whatever the threat may be, we can label it as a malicious adversary. And it's important to gauge the effects a malicious adversary may have on the estimation task or on the metrology task. Maybe they're interested in just learning the unknown parameter, despite it could be private, or they could bias it for their own gain. Whichever it is, or whichever the threat is, it's important to incorporate a cryptographic protocol which addresses the threat, but at the same time doesn't affect the underlying metrology problem. And so this work is partitioned into a series of papers, or in a series of 3 papers. In the first one, we focus on quantifying the effects of a malicious adversary. And to do this, we focus on the variance in the different settings. So variance is probably the biggest figure of merit within quantum metrology. It tells us how well we can estimate an unknown parameter. So here we bounded the variance in the cryptographic setting, and by cryptographic setting, I just mean a potential malicious adversary and the ideal setting, i.e. no malicious adversary. And we bound the difference with respect to some quantity epsilon, and epsilon is can be related to the protocol adopted to thwart any sort of malicious adversary. It can be related to the soundness of said protocol. And then in the first paper and the second paper, we focus on constructing different protocols. And so in paper number 1, we look at protocols for unsecured quantum channels. And in paper number 2, we look at protocols for delegating parts of the metrology task to an untrusted party. So for example, here Alice wants to perform or estimate some sort of unknown parameter conditioned on some unitary, and Alice doesn't have the necessary hardware to initialize a quantum state or measure a quantum state, and has to delegate it to Eve, who is untrusted. But using some random Clifford, Alice can actually detect with high probability any sort of tampering Eve may have done, while also keeping the unknown parameter private and unmeasurable by Eve. And so all of the protocols we construct can be executed with local Clifford gates. This is so that it would be somewhat implementable with near-term quantum hardware. And with this restriction, we see that we can maintain the same level of precision in the ideal case using only a quadratic increase in the number of resources. So here I mean by resources the number of qubits or the number of quantum states. And in our most recent work, we focus on the quantum sensing networks I mentioned earlier, and we ask the question of, well, what happens if some of the nodes are dishonest? And how can we protect the information pertaining to a local node to the other nodes? And to do this, we quantify, or we devise some notion of network privacy, and then a protocol to go along with it to guarantee approximate privacy. So as an example protocol, so this is a protocol taken from the first paper for using a unsecured quantum channel. So here Alice and Bob want to do some sort of metrological task, and they need to exchange information over a quantum channel, or an unsecured quantum channel. And this can be done using a form of quantum message authentication, where now Alice constructs an input state, which is a mixture of blue circles, which are the qubits used for quantum metrology, and purple triangles. And these purple triangles are at random indexes, L1 through LT, which are traps. And these traps are initialized in the ket 0 state and will eventually be measured by Bob. And before sending the row in through the quantum channel, Alice will perform some sort of Qcrypt operation. And upon receipt, Bob will perform the inverse of the operation to decrypt the message. And excuse me, these encoding and decoding gates are indexed by some classical key K, which we assume Alice and Bob share a secure classical channel. And when Bob measures all of the trap qubits, if they all measure 0, then with high probability, there has been no tampering with the quantum state. And if one or more measure in the state 1, then necessarily Eve has tampered with the quantum channel, and they discard the rest, or the quantum state. And going back to this quantifier, we have epsilon is proportional to the number of blue circles and inversely proportional to the number of purple triangles. So if the number of trap qubits greatly outweighs the number of metrology qubits, then this difference is almost 0, and thus the level of precision in the cryptographic setting is almost the same as the ideal setting. And if you want to learn more information, I encourage anyone to follow up on these papers or contact me directly. I'd be more than happy to answer any questions by email or have a chat. Thank you for listening.